For us normal people, -30 or 40 degrees Celsius is already our limit of survival. In Russia's Oymyakon, the local minimum temperature is -71 degrees Celsius. Even so, it is still inhabited. Compared with space, the temperature of most of the places that we just mentioned above can be regarded as a stove. First of all, for example, on the Moon, an American lunar probe found a hole with a temperature of -248 degrees Celsius. Another example is the well-known cosmic background radiation. The temperature is very low, only 3 Kelvin, only 3 degrees Celsius higher than absolute zero. But these are far from reaching the lowest temperature. In today's video, we are going to explore the coldest corner of the universe. What is temperature? Macroscopically, the temperature is a measure of how hot or cold an object is. It is a noun. But at the micro level, it may be more accurate to use verbs to define the index to measure the thermal motion of matter and microscopic particles. It is difficult to show the temperature in space. If you take a thermometer into space to measure the temperature, what will it measure? The high probability is that the specific degree cannot be displayed. For us, the temperature is hot and cold, but if you go deep into the micro world, the temperature is actually the thermal movement of molecules. The higher the temperature, the more intense the thermal movement of molecules. The lower the temperature, the less intense the thermal motion of the molecules. According to the uncertainty principle, when the molecule hardly moves thermally but vibrates in a small range, it will reach absolute zero. This temperature is -273.15 degrees Celsius. Therefore, the temperature value of absolute zero is also obtained from the thermal motion of the molecules, and there is such a strange value. Here we have to pay attention to one point. This is the result of a large number of statistics, which means that to measure this temperature, a large number of molecular aggregations should be measured. Except for celestial bodies and surrounding areas, the number of molecules is extremely small. In 2013, through the data sent back by the Planck satellite, scientists learned that the universe is not curved on a large scale. And based on the principles of cosmology and general relativity, they calculated the average density of the universe. If we regard all matter in the universe as hydrogen atoms. In fact, 99% of the elements in the universe are hydrogen and helium. The average density is equivalent to less than 1 hydrogen atom in 1 square meter. This degree of emptiness is a vacuum that no laboratory on this planet can create. In addition, there are many places in the universe where a large amount of matter gathers, which leads to a smaller density in other empty places. Therefore, with such an open space, you can't measure any temperature at all with a thermometer. And the reason why we can obviously feel cold and heat on Earth is that the Earth is a celestial body with a large number of material particles. There are enough microscopic particles to make us obviously feel cold and heat. Is there a temperature in space? In fact, there is, but this temperature is not absolutely zero. How much should it be? It's actually 2.7 K. That is 2.7 degrees higher than absolute zero. How is this obtained? In fact, this is related to the Big Bang theory. It is said that 13.8 billion years ago, the universe originated in a Big Bang. After 380,000 years, the temperature of the universe dropped to about 3000 K, and neutral atoms began to form. The waste heat is propagated in the universe in the form of electromagnetic waves and becomes the background radiation of the universe, spreading throughout the entire universe. It has continued to this day, and the temperature has dropped to 2.7 K, which is also known as the cosmic microwave background radiation. In the early 1960s, Penzias and R.W. Wilson, two engineers from Bell Labs in the United States, established a high-sensitivity horn-type receiving antenna system in order to improve the satellite communication. Then, they discovered that no matter what season, they can always receive background radiation all over the sky. Later, this was also confirmed as cosmic microwave background radiation. They won the Nobel Prize in Physics in 1978. However, the early equipment was relatively rudimentary, and the measurement of the cosmic microwave background radiation was not meticulous, and no specific details were reflected. Later, various countries successively launched different detectors to observe the cosmic microwave background radiation. The latest Planck satellite even ran into the Earth's orbit, moving around the Sun. In this way, the interference of the Earth was eliminated, a large amount of data was obtained, and cosmic microwave background radiation with the highest accuracy was obtained. Therefore, the existence of cosmic microwave background radiation is unequivocal. Nowadays, cosmic microwave background radiation can tell scientists how the past, present, and future of the universe will evolve. Space temperature is not absolutely zero, but 2.7 K. This is determined by the cosmic microwave background radiation. But at the same time, because the space is really wide and the density is too low, the temperature is based on the statistics of the thermal motion of a large number of microscopic particles. Therefore, people or thermometers cannot feel the existence of this temperature at all. Where is the coldest place in the universe? Although there are a large number of stars in the universe, space is actually very cold, and its average temperature is about 270.42 degrees below zero. The lowest temperature, in theory, absolute zero, is 273.15 degrees below zero. This is the temperature of the microwave background radiation that pervades the entire universe. In addition to the artificial low temperatures achieved in the laboratory, the coldest place astronomers have found in the universe is a nebula named Boomerang, which is surrounded by dying stars. It is located in the constellation Centaurus, 5,000 light-years from Earth. The temperature of the nebula is only 1 degree above absolute zero, that is, 272.15 degrees below zero. In appearance, it looks very much like a nebula after a supernova explosion, but in fact, the Boomerang Nebula is a planetary nebula. Because the mass of the original star is not enough to form a supernova explosion. After the red giant age, the abandoned shell formed a nebular structure. In general, the size of a planetary nebula is smaller than that of a supernova. The speed of diffusion is relatively slow, about 150 km per second. The Boomerang Nebula is the precursor of the planetary nebula. This is a young nebula with a dying star in the middle. The structure of the star is already very unstable, and it is ejecting high-speed gas at a speed of 164 km per second. As these gases move rapidly in space, their volume expands rapidly. This causes the temperature to drop rapidly. Here's a little explanation of the principle that the expansion of the gas volume causes the temperature to drop. Because the volume of gas expands, the pressure of gas drops, which slows down the thermal movement of gas molecules. Temperature is used to characterize the speed of molecular thermal motion. The slower the gas molecules move, the colder the gas is, which is why the temperature of the Boomerang Nebula is even colder than the microwave background radiation left by the Big Bang. This hourglass-like structure of the Boomerang Nebula is 31,000 kilometers long. It's about 20,000 astronomical units. This is due to the loss of material when the central star dies to the white dwarf stage and can no longer bind the outer shell. This scale will continue to expand in the future. According to the observations of the 8 mm radio telescope, the minimum temperature of the Boomerang Nebula is about 272.15 degrees below zero. It's only about 1 degree centigrade above absolute zero, but it will lose the crown in the future, because it spreads. The rapidly expanding gas cloud is being illuminated by nearby stars. This will allow its temperature to rise slowly and eventually reach at least 2.73 K. But in about 5 billion years, our Sun will go through the same process. At that time, the hydrogen fuel in the center of the Sun will run out, the structure will become unstable, and the Sun will continue to throw gas into space. As the Sun expands, it will become a red giant. Soon after, the outer gas of the red giant was thrown into space, forming a planetary nebula. The center collapses into a white dwarf and cools down in the universe. Well, that's the end of today's video. What do you think about the video content? Welcome to leave a comment.